Thanks. Yeah, please. Please. Right. So let me just remind you of the notation from last time. So we had the metric tensor Mn, which was the diagonal of 1, 1, minus 1, minus 1. And so that would be S spatial dimension and T temporal dimension. And of course, S plus T would be the dimension D of space-time. And the other thing we defined, so was we had this number n, which was always given by the integer part of the half dimension. This is very important in Spinor and Clifford algebras. And then, of course, the convention for the Clifford algebra was that gamma n anticommutator was equal to 2 eta mn times the unit matrix here. Right. So that was basically what the definition that we started from. And then the other thing we discussed, that's this half string basis, the half string picture. So let me also quickly remind you of that. So this was this meeting is being recorded. Continue. Good. So let's see. So we had these half strings, and they were given in the we started in the Euclidean signature. I guess that's a C, not a K. Euclidean signature. Then we had the gamma EJ1, and we had the gamma EJ2, and then we had in odd dimension we also had a gamma star, which is like a gamma 5. So there was it's like this. So theta, it's the sigma 3 tensor j minus 1 times, and then it was tensor sigma 1 tensor sigma tensor unit matrix 2 by 2 unit matrix n minus j tensor n minus j times, and then we had a sigma 3 tensor j minus 1 tensor sigma 2 tensor 1 2 by 2 tensor n minus j, and then we had in odd dimension we had sigma 3 just tensored n times. So so the point was that you should think of sigma 3 as the string and sigma 1 and sigma 2 as the end of the string. So it is something like we so the last sigma star would just be a string, and this one would be a string up to sigma 2 position, and this would be a string up to sigma 1 position. So they would stop at it goes from 1 and up to n, and so this would be like this would be the jth position we have written here, like that. Does that make sense? And then the idea is that sigma 2, we want to commute all of these guys. Well, if the first thing is we can see is that when we just multiply with itself then the sigma 3 squared and sigma 1 squared becomes 1, so it just becomes 1. So when we square all of these, we just get the identity as we should from, so they mimic at least the diagonal part of the Clifford algebra. And the off-diagonal part, that is really the nice thing of these half strings. And the point is basically that the sigma 3s, the string, commute with the sigma 3s over here. The only thing that doesn't commute is when the sigma 1 or sigma 2 hits a sigma 3. So here, of course, this must be two different J1 and J2, say, we're talking about. Then the point is that, say that J1 is less than J2, then the sigma 1 would meet a sigma 3 inside the half string. And when sigma 1 meets that, it would anticommute with that sigma 3. And therefore, these two elements would then anticommute. Does that make sense? And of course, it doesn't matter. Here I have sigma 1 and sigma 2 here, but it could actually be sigma 1 and sigma 1 also. And the same phenomenon will appear. And what that does is that all the off-diagonal elements of the Clifford algebra, it just says that all of the gamma matrices should anticommute. That is precisely what this representation does for you. So this would be our atom model. I mean, our starting point. So if people don't understand this, then we should stop. I mean, this is really important that you understand that we mimic, or we realize the d-dimensional Clifford algebra in this way. Are there questions to this? And of course, in the Euclidean signature, everything squares to +1. So now we have to also get to the other signatures. But first, I just want to make sure, is this crystal clear, or is there something, I'm not quite sure about this. People are very quiet. Some people are nodding.
I think it's more or less okay.
Yeah.
I guess it depends on how you will use it. Then I guess I'll know if I completely understand it or not.
Yeah, I mean, of course, one thing that's crucial in this picture is that you should remember how to multiply tensor products. So it's, of course, in this construction is absolutely crucial to know that when you take the A tensor B multiplied with C tensor D, then this is equal to AC tensor BD. Of course, this rule you should know. And of course, the generalization to n-time tensor product. So the first sigma 3 only meets the first sigma 3 here, and so on. Is it clear? Can we continue? So if you is okay with that, then we can now trivially mimic arbitrary signature. So the arbitrary signature is basically just that we put in some i's in the temporal directions. So gamma m is an arbitrary signature. So then we just take the Euclidean guys we had before, and then we will just say gamma m is equal to the Euclidean guy, or I times the Euclidean guy, if eta mm is +1, and if eta mm is -1, then we put in a minus to correct that. Is it clear? So this was what we did last time, plus some more about Clifford algebras. But today we will not focus on Clifford algebra. We will focus on representations of the spin representations. Well, they could also be spin representation of the Clifford algebra. But of course, many times we are just interested in the representation of the orthogonal group. So now comes the question of how do we, so one important thing in the classification of representations, whether we can make Majorana and all this stuff, is that we need to have a charge conjugation. So I'm thinking of so now here V will be some will be a Dirac spinor space. So I will define psi. I will write psi for a spinor, and then I will write that J of psi will be the charge conjugation of psi, and I will implement that through some matrix J and complex conjugation like this. And the point is that V is, so this is charge conjugation that we are talking about, and V in this case is the spinor space. So psi belongs to V, and so this would be Dirac, what is usually called a Dirac spinor. But to be perfectly honest, the point is now that this actually acts on the Clifford algebra. It has, of course, the same dimension. So we can actually think of it as a pinner, a Dirac pinner. And so if you recall that the pinner group, so the spin group was was given by the product of all the units of the gamma matrices in different products, different order products, and when we go to the sorry, that was the pinner space, and the spinor is if you only take even products. So it just means that a Dirac pinner space is obviously also a spinor space, because it just means that we only, if it is a spinor space, then we only apply it to a combination of two gamma matrices. Does that make sense? So this is so strictly speaking, in general, it would be well, I guess a spinor is a little bit more general than a pinner. Pinner is also a spinor, but a spinor might not be a pinner.
What does that mean? It's just whether it's a representation of Clifford or of the SO, the spin n, right?
Yes, exactly.
But it's the same space always, no? Unless you further decompose into wild parts, but right. Otherwise it's always the same, no?
Right. But now we will impose conditions. Yeah, I think you're right. At this level, they're actually the same. But now we will now look at the charge conjugation, and this should be a charge conjugation should be a antilinear map. map J from this representation space into the representation space. Does that make sense? Does everybody know what an antilinear map is? So antilinear means that the complex conjugation it is conjugated linear with respect to complex conjugation, and that is of course completely written out here. We can of course think of a linear map as a matrix, but because it's antilinear, then we have to put a complex conjugation on here. Does that make sense? So you can see that capital J is sort of the matrix representation of this linear map. And then the other thing we would like is that, that this linear map should be G invariant. So we would like that when we act with our, last time G was the orthogonal group, or the SO plus S comma T over R. So G, this is the group I'm talking about, and we want it to be G equivariant this map. So we would like that rho of G. So rho is the representation of G on V. So rho runs from maps G into the endomorphisms. Well, you can say it's the same as GLV R, which sits inside the endomorphisms of V. Is it clear?
Is that, wait, it could be, it's a real group, but the representation a priori could be complex, right?
Oh, you're right. Yeah. Yes, in fact, yes. V is a complex space. Else it doesn't really make sense to talk about that. Yeah, so it's inside this and inside endomorphism for V to V. Yes, thank you. I was being sloppy or made a mistake. So this should be equivariant. So we would have to impose that it doesn't matter whether we take the charge conjugation before or after we act with the group. Does that make sense? And now we can just use the definitions. So J, so this is the same by definition, equal to, see if I can do it correctly. This is equal to J, and then I would have complex conjugation, G psi, complex conjugation, I guess. And here I would get that this is equal to rho G J psi star, like this. And is it clear? So here we are just using we write it little j into capital J, and then we can get a condition for capital J, which is that rho minus G minus first capital J rho G should be equal to J. So I think there's something wrong. There should be a star here. So I think now it's correct, rho J, and I just move the rho on the other side. Or if I want, I can also rewrite it into rho G star equal to J minus first rho G J, like this. Is it clear? Stanislav is nodding. The point is now that the last condition here, this is exactly the condition that the V complex conjugate representation, I call it V bar because I think nobody else would call V bar for other than the complex conjugate representation. It is isomorphic to V because there exists apparently a matrix J such that these two representations are conjugate to each other. Does that make sense? So, so this in mathematics.
Can I ask?
Yeah.
So is this something that you assume, or is it true for every Dirac space that there exists such a J that this is true, or do you have to?
Yeah, this is something I think this would be like some kind of axiom in quantum field theory that we know what charge conjugation should be. Mm-hmm. So we will assume this, that there exists such an antilinear map, mm-hmm. And I guess I implicitly also assume that it's invertible. So we have that.
Thanks.
And so this we will later discuss when V bar is equal to V. This is what mathematicians they call this real or pseudo-real. We will later see that that's actually the case. But it turns. But for now, when the complex conjugate representation is the same as or isomorphic to V, then we are in the case we call pseudo-real. And sometimes it's real and sometimes it's pseudo-real. So this is two cases I'm trying to write very shortly, as briefly as but it's really two cases, as we will discuss in a moment.
What are you referring to now? What is real pseudo-real?
When the complex conjugate representation isomorphic to the representation, then we will say representation is real, mm-hmm. or pseudo-real.
Okay.
Yeah. It's two cases. It's not that it's not real. That's sometimes called pseudo-real. It's two distinct cases. And so now
wait, sir, can you repeat that? Like now for any charge conjugation like this, whether it squares to 1 or not or -1, it's true that the complex conjugate representation is isomorphic to the right. So it's still pseudo. It's always pseudo-real.
Yeah. You're right. I think. Yeah, we get in. Okay, but I don't want to get into to the square condition yet. But you're right. I mean, formally there is some implicit assumption about the square, what square of J is.
So as for now, it's just. This is just general charge conjugation.
Yeah.
And this is pseudo-real, right? For any charge conjugation, we just shown
it's pseudo-real or real.
What does real mean then? What is the difference here?
It's a definition. Well, okay. You want to know what it exactly is, but that's exactly what I'm going to explain in an hour.
Okay. No, it just seems like now there's two definitions: pseudo-real and real.
No, I just want to prepare you for what's going to come. So I'm claiming that this will turn into two conditions or two cases, and one is pseudo-real and the other one is real. And then I will also inform that this is often in the math phys literature is called symplectic Majorana and Majorana. Okay, and then I have here we are only talking about representation theory. So here both of this I would say is like the mathematical literature. I guess this is the actual mathematical literature, and the symplectic Majorana that is like some physics-like words that they associate instead of pseudo they call it symplectic, and real they call Majorana. but it is one-to-one. But it turns out that in the physics literature, sometimes we impose more conditions of being a Majorana and symplectic Majorana. So therefore, what we're talking about, and today we will mostly talk about the mathematical definition, which I will return to in a moment. So this is the representation definition or the math definition. But I should already warn you now that in physics, it's not enough to be symplectic Majorana or the pseudo-real in the math sense. So the physics would divide into two cases, and there are two cases already, so there will be like four cases. So there will be something that that physicists would call symplectic Majorana, and then there will be some other case, the other half of that they will call pseudo symplectic, and that would be a distinct case, symplectic Majorana. And the difference is that so physicists usually have some more criteria before they would say that this should be a symplectic Majorana, and one of them would be that you should that you should be able to write a mass term for the Majorana spinor. If you cannot write a mass term, then you are in the pseudo Majorana case. So there should exist a mass term before physicists will call it a Majorana. Or another way of saying is there should exist a representation where the gamma matrices are real.
Is that is this equivalent to saying that the charge conjugation is equivalent with respect to full Clifford, as opposed to just spin?
Moment. So that's that is there exist a real gamma matrices. So you can our gamma matrices are not real because we have sigma. Actually, the only non-real is sigma 2. There's an I there. Well, and then there's more I's if we are in different signatures. So we have here, so there exists real gamma matrices, and another is exactly what Andre was referring to, is that they exist a pinner that they work at the pinner level, so they are Majorana pinners, so to speak. So that would be another one. And so this turns out to be equivalent, but I don't think we will have time to look at that. Of course, there's other things that a physicist would be interested in. Does it make sense to make Wick rotation? Things like that. So, but today we will just look at the mathematical representation theoretic discussion, and then maybe if we have time look at the more. But we will start just with the first thing here. The other thing we can say is, so we can also use the other, so this condition here clearly shows that the complex conjugate and the conjugate on the representation are the same, but we can also use this condition here, which basically tells you something about how we can now expand the representation in rho g. We can think of that as an exponential of some Lorentz matrices, or I call it Lorentz, even though maybe it's the signature could be different than Minkowski. I don't know what to call them, so I just call them Lorentz matrices. So sigma mn, which you might remember was equal to half gamma mn, where this was the anti-commutator of two gamma matrices. And then I guess multiplied with some generators or some parameters omega mn like this. So we can write it like this, and then we can expand this out and assume that omega is infinitesimal. And then we can expand out this condition here, and I claim that if we do that, then we would get that the gamma star mn should be equal to j minus sigma mnj. Actually, maybe that was actually easiest to do from that one. Yeah, actually that's also easiest to see from that one. Does that make sense? People are nodding. So we get this condition here. And then it is natural there is a sufficient condition. Sufficient condition. And that is, so here let me remind you that sigma mn is the half gamma mn, and that is of course half times half, that's a quarter, anticommutator m, anticommutator n. So that was how we defined the sigma matrices, capital sigma matrices. So sufficient condition for this to hold is apparently that we choose gamma j minus first gamma mj to be equal to plus minus gamma star m. So if this is the case, then clearly this is the case. Does that make sense? So if we can impose this condition on the gamma matrices, then obviously the sigma matrix would also satisfy this. And we can even change the sign here, because there's two gamma matrices. It's the even part. So the point is now that if we choose the plus sign, then that corresponds to that we actually have a pinner representation that would satisfy this. And if we choose the minus sign, then we cannot lift to that violates so we don't have the relation if they use a minus. So the plus sign corresponds to the pinner, and the minus sign, both of them correspond to Spinors. So I guess this one corresponds exactly to this pseudo pinner case. Okay. So we will try to see if we can make this work. And there is a solution to this. So the solution is in terms of J. How should we take J? So there's actually two canonical solutions. So there's one I will call J imaginary, which will be the product of all the matrices, imaginary matrices, gamma matrices, from M, where M runs from 1 to D, and let me put an arrow to say that it has to be increasing order that we put it in. So so I claim that this would be so I define J to be one solution. J, I claim that this when we take the product of all the imaginary gamma matrices, then this would actually satisfy this condition here. And I guess I already should already reveal that there's another one which I will call real, J real. I don't know how much space I need, but there will be another one where I need J real is defined, and then I will do the same definition, but then I will use all the real gamma matrices. D. Gamma M. Okay, so the first thing we should find out is how many imaginary gamma matrices do we have. So let me call the number dm, and then I will also call the number here for d real. So how many do we have of imaginary gamma matrices? So I claim that this number is given by n because we have n gamma 2 matrices here that have a sigma 2 in it. So we have n of those. So therefore, there will be n here. But now, because we are an arbitrary signature, we now have to take into account that we might have rotated with a factor of I when we go when we introduce imaginary, time directions. So so now we would have to. So that two things can happen. We can so if some of the time directions are in some of the sigma 2 directions, then we are taking away an I on sigma 2. So let me call the time directions that is in the sigma 2 direction for even for 2. And then we have to add the time direction, odd time directions, which are related to sigma 1 when we have a time direction in sigma 1 direction. So I call that T odd. And the reason why I don't call them T2 and T1, which maybe would be natural, that's because there also could be a time direction with respect to gamma star in odd dimension, and that's sigma 3. That's also odd. So I mean, if you don't like to call it T even, you may want to call it T2 and T13. So the point is that I would have to correct the for Euclidean signature the number of imaginary gamma matrices n, but then I would have to subtract and add depending on where I put the time directions in the 1 or the 2 direction. Does that make sense? I see Standard is nodding. So that's one thing, and then there's a similar calculation here for the other one, and since there is now d minus n gamma sigma 1 matrices like that, that's and then d minus. So remember that. Yeah. So the point is that the total number should be d, of course. If they're not imaginary, they're real. So therefore, it's d minus n here. But then we have to make this in the opposite order. So now we have to subtract the t odd, and then we have to add the t even. This is supposed to be odd, and then t even. Does that make sense? So that is so much for how many of these matrices we have. So now the point is now that we can try to calculate what is J im minus first I probably need a little bit more space, so maybe put it all the way up. J im minus first, and then I have gamma m and J im like this. So now, so here comes a standard argument. So the point is now that that the gamma matrices, all of the gamma matrices, they anti-commute except if in themselves, then of course the square to 1 or minus 1. So let's see. So we have here gamma m. So there's two cases. Either gamma m is an imaginary matrix. Actually, let's say that gamma m is real. If gamma m is real, then it certainly anti-commute with all of the imaginary matrices. So therefore, we would get a minus 1 to the d im here, and then we would get gamma m was real. So if gamma m is real, then this is certainly true. Does that make sense? Is it clear? So since it was real, I can put this complex conjugate for free. So now the trick is now that if it had been imaginary, then it is equal to one of the matrices inside the J imaginary. And therefore, it would anti-commute with one less. And therefore, it would be d im minus 1. But then I have to put I put a complex conjugate here, and because it's imaginary, I get an extra sign. So this is still true. So this is the trick. It both work for real and imaginary. Does that make sense? And the same. The same we can do for the real. The argument is just a little bit the other way around, but it's still the same. So I take J minus first real gamma m J real equal to minus 1, and then so the point is now that if we take an imaginary, then imaginary will commute with all the reals, so that would get d real here. And then I want to write a complex conjugate. So therefore, since it's real imaginary, then I have to put in an extra minus. So it becomes this equal to minus that. And then it works. And then you can also check that if it's real, then there's one less that it anti-commute with, and then the minus 1d is absolutely correct. And you now see that that's actually a solution to the equation we were trying to find a solution to. So it's a solution to this equation here with some signature here. So we have that. So we see we have found two canonical solutions to how to construct such J matrices. Is it clear? And then there is a little bit of algebra to write it in a nicer form. So here I will write this as minus 1, and then the point is that this is Boolean algebra. So we are only interested in mod 2 because it's minus 1 to something here. So and since it's mod 2, I can change the plus here to a minus. So I can subtract 2 t odd. And therefore I can write here for free n minus t gamma star m. That would be the same. Does that make sense? And the same I can do here with real. I can write this as minus 1 d minus n minus t for the same reason, gamma star m. So it apparently it doesn't matter where we put the time directions. This would still work. It's independent of that. It just depends on the total number of time directions. The next thing we can do is that this is the same as -1 to the d half minus an integer t. So n is the integer part of d half. So I can for free write it like this, gamma star m. And this one I can rewrite as, so d is s plus t. So I can write this as s minus t half integer part. Does that make sense? And then I forgot the gamma star m here. So the point is that we now see that we have a symplectic Majorana pinner. A pinner is exactly when this sign is plus sign. So the conclusion is for later that pinner occurs if and only if s minus t is equal to 0 or 1 mod 4. If we use J imaginary, so if we construct our charge conjugation with the J imaginary this way, then we can get pinner representation if space-time minus s minus t is 0 or 1 mod 4. In that case, this would be 0, and then we would get a 1 in front. And in 2 and 3, the other two cases, we would get the other case. Make sense? So now we have to do the same for this guy. It's a little bit more annoying, but let's do it anyway. So this is equal to, this is equal to the minus 1 d minus d half integer part minus t. Okay, so now there's a trick, and that is to write this as, see if I can write it. This is equal to, I get this, so I would like to get rid of the minus in front of this integer part. And I claim that that's actually the same as minus 1 d plus 1 minus d half minus t. So I claim that minus d half over 2 is the same as plus 1 minus d half. And I think this takes a little bit of thinking, but for now you can think. I basically claim that you can think of this mod 2 in dimension. So you can extract. You can think of d as rest class 2. So either 0 and 1 plus something even. And the even part would be an integer, and it's not difficult to see that the even part would give the same factor here. So we only have to basically check 0 and 1. So the point is that if this is, if d is 0, then I get a half, that's 0, and if d is 0, I get 0, that's perfect. And if d is 1, I get 0 here, and d is 1, I get 0 here. So it's actually allowed. Does that make sense? So, so once I have that opposite sign, then I can do the same trick with since these are integers, I can put it inside the integer part, and what I get is, and I think I dropped a minus sign. There was a minus sign here, which I forgot about. So this is equal to minus that, and it's equal to minus that, and it's equal to minus that. So I claim that at the end of the day, this is gamma star m, this becomes equal to -1 s, and then I bring up the minus upstairs. So this explains why I now get -1/2. So I get st -1/2 absolute integer part m star. And now this here, so now we get the condition. If you use Pinner here, the Pinner condition here becomes equivalent to that s minus t should be equal to 1 or 2 mod 4. So it is slightly shifted from the other case. So this means that we can explore different dimension by using, I mean, if we want to have Pinner representations, we can use it. It sometimes matters whether we use all the imaginary or all the real to create the J matrix. Okay. So I guess the thing that I would not go into is that this is more or less the only possibility. So these are the only two possibilities. And yeah, and while we are at it, then let me also now add. We will also want to know what happens when we go to in even dimension. So parity in even dimension, even dim. Then we can look at how the gamma 5 or the gamma star act on gamma m, gamma star minus first, and I claim that that's equal to minus gamma m. I think we saw that before. Well, I mean, a cheap way would be say that we basically saw that it was proportional to sigma 3 to the n, and that it's equal to this guy, of course, up to some factor, but the factor goes away because of -1, and then because in odd dimension it should anti-commute. This must be true, and then we want to know what happens to gamma star. How does gamma star interact with J im, or the real part that we have constructed, gamma star minus first here. And it turns out that is this equal to, this will be equal to -1 d im, or real part. I'm trying to do two cases at one time, times J im real part. So why is that? That's because we know that gamma star has this relation with any gamma matrix. So therefore, J im and real, they are constructed out of d im real parts of that. So we will get this many signed. So we get this here, and this is equal to, as we saw before, this is equal to -1 n minus t J im real, and this one is now we actually in even dimension, so it's for similar reason as before, it's s minus t half, but we don't need to have the integer part. So we have this J im real. So we have this this condition. So what this tells us is that when S and T, S minus T is equal to 0 mod 4, then we have two conditions. So maybe I should start with the other case with S minus T is 2 mod 4. So this is only two cases because we have even dimension. So therefore S minus T is always even. So there's only these two cases. And in this case, yeah, well, okay, so S minus T is equal to either 0 mod 8 or 0 mod 4 mod 8, 4 mod 8. And so this case will be Majorana Weil. And this one will be symplectic Majorana Weil. And the other case, here we will have Weil spinors are complex representations. Where so how is that? Let's see, when S minus T is 0 mod 4, then this is +1. So this means that in this case, the complex conjugation commute with the parity, and in this case we can impose the Majorana or the symplectic Majorana. I forgot why. I guess I still to actually see the difference between these two, we have to discuss the square. So I will not be able to tell you this yet. And in the other case, we see that if S minus T is equal to 2, then mod 4, then these would anti-commute, and you cannot impose both structures at the same time. So so that's the case, and so now we can write down this will be the result, but now of course I have to explain what all of this means. So let me just write the table that we have gotten. So if I write S minus T and then J im and then J, I hope that I can have 8 lines down here, J real, and then gamma star here, and so this will be the main result. So we would have 0 mod 8. So it's, I want to have 8. So you have a 1, 2, 3, 4, 5, 6, 7, and then mod 8, of course, all of it. And then we have seen that when we get to this condition, we would get Okay. Now, yeah, I'm jumping ahead. I should, of course, now explain where. Yeah. So I was too fast with this parity. This came a little bit too quick. We will return to this. I of course have to discuss what happened to the square. So let me maybe take away more or less this. Right. So so I forgot, of course, to discuss involution. So we of course would like that when we apply the charge conjugation twice, then we should somehow get back. So the charge conjugation. So here we can have pseudo involution of the charge of J. So we have to discuss that first. And so the point is that we now apply the charge conjugation twice. And by definition, that was equal to J psi conjugation like that. That was how we define conjugation. And then we have to do it twice, so it becomes equal to J star psi like this. And then the involution condition we will set up is we will call it plus minus psi. So we will allow that there could be a minus sign here. And so pseudo now, so that's a different version of the use of pseudo here. So pseudo here means that the minus here, that it squares to minus. And if it's a plus, then we would say it's a genuine involution. And so this is equal to, clearly we get that J star matrix should be equal to plus minus 1. And this is, well, actually, so this is exactly the same condition as being pseudo real. So yeah, so the pseudo again refers to the minus. So now, this will be exactly how we distinguish symplectic Majorana and Majorana. So if it's +1, then we call it Majorana. If it's -1, then we call it symplectic Majorana. Okay. And so now we have to calculate for our two canonical choices. We would like to know whether they would give us pseudo-real or actually real representations. So we would have to now do this calculation for, we would have to calculate what is JM complex conjugate. And we will have to check, is this +1 or is it -1? So this is a little bit annoying, but it's doable. So the point is now that we would like to, yeah. So what we have here is so we have a product of imaginary gamma matrices. And here we have another product of the same product, but it's of course complex conjugate, so of these imaginary gamma matrices. And this guy would be the same, and this guy would be the same. So the annoying thing is that we would like to contract these guys, because we know that the square to 1 or minus 1. So we would like to have them next to each other. So therefore, we would like to invert we have to reorder the set here of n elements. So we will need to have, and they're anti-commuting all of this. So we would need to have a formula that tells us if you have n elements and you want to replace 1 to n, well, maybe I shouldn't call it n because n is this fixed holy sacred number. So maybe I call it m. So we have m numbers here, and we want to rewrite it into m up to 1. And they are anti-commuting. So we will find out how many signs does it take to pick up that. And I claim that that's the same as the first I have to permute m minus 1 term times, and then do it by m minus 2 and m minus 3. So I see that this is basically the triangle number where I have to sum I equal 1 and up to m minus 1 of I. I have to make this sum. This will give me how many transpositions I have to do, and it costs a minus every time. So, and this sum is the same as, I claim it's the same as, is it m minus 1 over 2? I think that's correct. I see that at least Patrick is nodding. Everybody else is not. Okay, so the point is it's this number here. And then you can also convince yourself that this number mod 2 is the same as yeah, so basically we are looking at minus 1 to this, minus 1 to that, and I claim that that's actually the same as minus 1 to m half integer part. So I claim that there is such a relationship. So basically it says that if you want to switch 2 elements, it costs a minus. If you want to switch 3 elements, then you have to do, let's see, so 2 and 1, you should also get a minus. But if you want to have 4 elements and 5, it should be plus, I think. So does that make sense? So m2 over 2, that's a minus. 3 over 2, that's still 1, that's a minus. Yeah, so there is, you can use this formula to see how many ways. I haven't thought about, I guess there is an argument by going into even and odd of this. So, but anyway, this is the factor here. So what we get is that the idea is now that I'm turning around all the half of these, so I get the same kind next to each other. So and that cost me a factor. Yeah, actually, maybe it's easier to write that as dm and then dm minus 1 over 2. So that's one thing. So now I have turned them around, and then I want to start contracting them. Now it's nice, and I claim that I then get another additional dm, because first of all I have a complex conjugate. So and since they're all imaginary, then I have also dm minus signs for taking the complex conjugate. So I plus this guy. So and then I know that some of them will not square to plus 1, but square to minus 1. That's the t. That is actually the TO, the T odd. Here I have to add T odd here because every time, so the imaginary guys, there would be a I thought that this was clear. So it's basically it's basically these guys that I had to add here T odd, that these they would square to -1, and so therefore I should put in a T odd here. So now I get confused about why this is okay. So I have turned them around, so they're next to each other, and then I have I also put this, and so now I'm a little bit confused why there's no interaction with this, but okay, I think I cannot, I don't think I can reconstruct it now, but so assume that I think this is correct. So this is the result here. So yeah, okay, what is missing? Okay, yeah, I guess it's because these are not really there. So so we are looking at n minus TE guys that we did not change a sign on, but there's a TO which we put in an extra I minus here, so that we have to account for. So there's a TO here. And yeah, so and then this one we can, so this is proportional to the identity. And then we have to simplify this. So this is equal to -1 dm. Okay, and then there's a trick here that clearly we can add. There's a -½ dm, so I can take this inside, we write it dm +1 over 2 plus t0, t odd. And the next thing we can do is that this one we can simplify to, so this one actually we recognize as just shifted with one of this guy. So this becomes equal to dm +1 over 2 integer part plus t0, t odd. We have that. And this one I can write as minus, so this is equal to 1. So this is equal to -1 And then I get the dm, I will just write as n minus te plus to plus 1 over 2 plus plus oh, and I changed this to minus. Instead of plus to, I can write minus to for free. So I have that. And then the point is I can now put, this is an integer, I can put it inside here. So therefore, the plus to half here minus to actually simplifies into minus 1 n minus t plus 1 half integer part. So we get that. And then we can write this as minus 1. And then I suggest to write this as 2n minus 2t minus 2 over 4 integer part like this. So we can write it into here. And then we can write this. And so this, I think, is maybe the most difficult part, that you can write this as d minus 2t minus 2 over 4. And this is clearly true when in even dimension, because then 2n would be d. But the point is now that in odd dimension, d would be 1 bigger, but everything here is even, and adding 1 will never, when we have divided by 4, turn over to another part of this integer part. So actually, I can secretly put in an extra 1 sometimes here, and you could not see it in the formula. So that is actually okay, and therefore this is equal to and this is equal to s minus t minus 2 over 4 minus 1 1 here. So we get this formula here, and so I don't know how much time have we used. So we started. Okay, so maybe I will simply just declare that we can do the same for J real. It's even worse than the other one, but it's doable since I'm running out of time. So if you do the same for this guy, then you get that this is equal to minus 1 s minus t minus 1 over 4 in integer part like this. So that is times the identity matrix here. So this is and the result is, of course, that we get that I did not write that down. Yeah. So now we can start to fill in the conditions. So the point is that according to depending on what this sign is, then we either get pseudo-real or real representation here, or symplectic or Majorana. So in the end, so I guess maybe I should start with saying, why do we get s minus t equal to 0? So when we have s minus t equal to 0 mod 4, then mod 8, then this one becomes this one becomes plus. So this is the Majorana Weil condition, and if s minus t is odd, is s minus t is 4, then I get 4 here minus 2, that's 2 That's 1 minus 2. Oh, it's 4 here. So this is 4 minus, so this is 2, that's a half. Okay. Okay, yeah, so for some reason this +1 should become +2 here, which would be +2 here, it should be +2 here. So now it makes sense. So, so we have 2, so when s minus t is 0, we get 2, that's a half, that's integer value is 0, so that's +1. So that is the plus here. And when we're 4, we get 4 plus 2, that's 6 over 4, so that's give me 3/2, integer value 1, so I get a -1. So that's the case I get the symplectic Majorana in that case. Anyway, so you can go through all of these cases, and the table that we get is the following. So we get M, S, 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 M, M. So clearly it's mod 4, so we get 4 after each other here, and the same with the real part, but it's shifted a little bit. So we get M, 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 S, 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 M. And in the real cases, we now get, so this M and S, of course, stands for symplectic Majorana or Majorana. And then let me put in parentheses when it's not a pinner representation. So this is not pinner. This is not pinner. This is not pinner. And here. So this is why I take this into account. Then we get this. And then when we also have gamma star, then we get Majorana Weil. And here we get a complex Weil representation. Here we get a symplectic Majorana Weil. And here we get a complex representation. So this is the main conclusion that you get these. But now let's, in the remainder of the time, let's discuss in more detail the different cases. So the first thing I want to do is I want to work the other way around. Unfortunately, I deleted this case, so I want to say that let's start with the case where V is equivalent, V bar is equivalent to V. Let's consider this case. And in this case, we know that so that basically means that the complex conjugate representation is of course given by rho G complex conjugate, and the equivalence here means that there exists a J such that rho this is equal to J minus first rho G rho. So so now we go the other way around. Now we are saying assume this. Assume this. And then we know that since they are equivalent, there must exist a matrix J that satisfy this condition here. And this condition we saw that this was the same as there exists a J, little j psi equal to J psi star, which was G invariant. This was precisely the condition to be G invariant and J invariant. Sorry, G invariant. So then the next thing is that we can write down that that this implies that rho G is equal to J minus first star. So I guess I'm taking complex conjugate of this guy. So I get J minus first, and then I get rho J star here, and then I get J star here. And then I can use this condition again. So this becomes equal to J star minus first rho G J star. So I get that this I get this condition must be satisfied. So we see that this matrix J star it must commute with rho of G for any G. And so now we will assume that the representation is irreducible, and then we will use Schur lemma, and therefore we conclude that J star is proportional to the identity. Does that make sense? So and now we are almost there, because J proportional to identity, we came from that J we would like to have a pseudo involution. So the point is, the first thing we can do is we can clearly scale J with a real number, real positive number. I guess it doesn't matter whether it's positive or negative. So we scale the J matrix. That would clearly not, if we have one J matrix, we could take another J matrix which is scaled. That would clearly satisfy the same. And therefore we can, without loss of generality, we can assume of generality, we can assume that J star is equal to plus minus 1. We cannot get rid of a minus sign because we want it to be real. But we can yeah, even if we chose a complex, then it would have no effect because of the complex conjugate here. So the point is that we might as well just have real scaling, and in real scaling we cannot get rid of a minus sign in this proportionality factor, but we can get rid of the overall size. So either it's plus or minus 1. So this is quite nice, because this completes the circle. So either we start with a charge conjugation which is a pseudo involution or evolution, and then we see that the complex conjugate representation have to be equivalent, or we can start the other way, and then we can derive this condition here. So this is nice to see that it goes hand in hand. So now, what time is it now? It's 32. Okay, so we still have some time. So now let me say a little bit more about the various cases. I guess the most interesting case is when it's, well, I guess we are mostly interested in the real case, not the pseudo real case, but the pseudo real case is actually quite interesting. So in the pseudo real case, so this is the case where the J squared is equal to minus the identity on our representation. So we have a pseudo involution. Then we can actually, it turns out that we can lift V, which is a complex representation. V is a C vector space. And we can lift this to a quaternionic representation. We can lift it to a quaternionic representation in the following way. So the point is that we can define an action of the quaternions J here. So this is a left action, group action, acting on psi equal to A psi plus Bj psi, where A and B are complex numbers, and psi belongs to the vector space. So now I have used J in two different meanings. J here is this antilinear map that squares to -1 on the Spinors Dirac-Pinner space, but here this J here is the second imaginary unit of the quaternions. So I'm using J in two different meanings here. Is this clear? And so here I have an action. So I'm acting with quaternions on the spinor, and then I claim it should be equal to that. So what we need to check is that the condition for being a quaternion action. So it shouldn't matter whether I first multiply two quaternions together and then act, or I first act with one quaternion and then act with another quaternion. I should get the same. So we have to check that that actually makes sense. So the point is that this is equal to A plus Bj C plus Dj. So here I have taken two quaternion numbers. Of course, it's implicitly understood on this side that J anticommute with the I that sits inside A and B. A and B are complex numbers, so it's understood that the anticommutator of A and I is equal to 0. That is how that is the meaning of this J, and of course it's also assumed that J squares to -1. But anyway, let's calculate this acting on psi, and I claim that that's the same as AC minus BD complex conjugate plus AD plus BC complex conjugate J acting on psi. So this, what did I do here? I guess I just multiplied out, and I moved the J through C and through D, and when I do that, I get a complex conjugate, and when I have two J's, I get a minus. Does that make sense? And then the next thing is we're now using the definition of the action. So this is by definition the same as A C minus BD star psi plus AD plus BC star J psi. So this is, here we have used the definition of the action, how this is supposed to act on that. That's the definition. And now the trick is now to rearrange this as successive application of quaternion. So this is equal to A C psi plus D J of psi plus B J C psi plus D J psi, like this. So here I'm just writing out in two, regrouping it in a different way. I guess I also applied J here. So now we use that J is an antilinear map. So when C comes out of J, it becomes complex conjugate C. And when D comes out of J, it becomes complex conjugate here. And then we apply J squared, which squares to -1. So we also get this minus here. So that was that. And I claim that this is the same as A plus BJ acting on C psi plus DJ psi. So you can convince yourself that when you use the formula here, this formula here, then you exactly get this formula. And then the last part is the same as A plus BJ acting on C plus DJ acting on psi. So here we see that we can either multiply the quaternions together before we act, or we can we can act with the quaternions successively. So it is in fact a quaternion representation. Quaternion representation. So that is quite interesting about the pseudo-real case, that there's secretly a quaternion acting. Okay, so now we can finally also talk about the Majorana reality condition, and that is, of course, this is the case where J squared is equal to the identity squares to plus the identity. And the condition is that we would say that J psi should be equal to plus minus. I mean, because it squares to +1, then the eigenvalues of J must be, it makes sense to talk about, to impose this condition. So this condition here, either plus or minus for the two sectors, yeah. So maybe I will leave it like that. This is the Majorana condition, and obviously we can change from the plus condition to the minus condition by changing psi to I psi. So yeah. So the plus minus here is not important. It's just different sectors. But more interesting is the symplectic case. So the symplectic Majorana pseudo reality condition. And in this case, it is there we have something that squares to minus the identity on V. And it does not make sense to impose something like this condition here. So what we do is we can yeah, I guess it's because in this case here we can basically define projection operators that we can clearly define projection operators that would take us to these two subspace. But this does not work when it squares to -1 here. So therefore we have to do something else. And the thing is, we will go yeah, so the other thing I want to say is that the Majorana condition, we impose that, and it basically splits the full vector space in two subspaces. So I mean, what we have discovered in this case is that the full Dirac spinor is reducible, and we can impose two irreducible parts inside that. But the same is not true for the pseudo-real condition. It is actually irreducible representation, and we cannot reduce it further. And the quaternions, in this case, sew it together. But what we can do is we can make a double copy. Sorry, I cannot speak. A double copy of V. So if we consider a double copy of V, so V plus V, then we can construct artificially another pseudo involution on that double cover. Let's call that omega. So so omega goes from V to the double copy of V here, and we want omega to square to -1 as well. So omega squared should be equal to minus the identity on V plus V. And we just take the simplest we can think of. We think of omega of copy 1 plus copy 2 should be equal to minus copy 2 plus copy 1, like this. And if we square this, it's easy to see that that this squares precisely to minus the identity. If we do this twice, it's like a symplectic action here, and then we can now take the composition omega composed with J plus J on the double copy, which then also goes from V plus V into V plus V. And the idea is that since both J and omega squares to -1, then when we take the composition map here, we get something which squares to +1. So this becomes an honest involution. Does that make sense? And so on the double copy, we can now impose, we can now split this in two sectors, where we can now impose something similar to this condition on the double here. So the symplectic Majorana condition becomes that minus j on psi 2 plus j of psi 1, which is the same as omega composed with j plus j acting on psi 1 plus psi 2. And then we can now introduce two sectors plus minus here on psi 1 plus psi 2. So this is not a reduction per se, because we first double up and then we split, but it is another splitting in some sense. So I guess I want to have plus here and then like this. So so we can do this construction, and so that's the best we can do, and that would be the symplectic Majorana condition. So I think this is more or less what I planned to say. Of course, there's much more to be said, but I think maybe this would be time to stop, and then maybe if there's questions.
Okay, thank you, Klaus, for a lecture. And do you have any questions?
Yeah, I have just one simple question. So you have the difference between the Majorana veil and symplectic veil. Symplectic Majorana veil, is it because there is some symplectic structure which exists only in a special difference between the S and T? Or is it because the representation then satisfies some condition which looks like a symplectic condition or something like that?
Yeah, I think it's because physicists usually they think they're thinking of this when you impose this symplectic condition. I think so. This is probably why they call it symplectic.
Okay,
Yeah.
so it's not that you would have some symplectic structure which only exists with special.
Right. I guess there is maybe someone would maybe think of. I mean, of course, there is some kind of. I think the most honest answer would be say yes, you're right. But of course, maybe this quaternion sort of speaks to some secret symplectic structure. I don't know. I mean, because you're basically undoing this that it squares to -1 with this artificial symplectic structure outside. Yeah.
Yeah. Okay. Yeah. Maybe what I wanted to know, is if there is some additional characterization to these representations other than.
Yeah.
What
No.
you
No.
just
I'm not aware. I'm not aware whether there is a symplectic structure just on V, so inside V. But of course, since it's a quaternion representation, of course this V must be divisible by 4 if we are talking real dimension. So maybe there's plenty of room for defining something antisymmetric and invertible.
And maybe also one more thing, but I guess it would be a stupid question. But last time you talked about this Clifford algebras, and when you have the classification of Clifford algebras, there is this formula or sort of this iterative
Yes.
formula that you can create, you know, the higher dimensional Clifford algebras, and you have this formula which tells you how to get a Clifford algebra from one which is 4-dimensionless. So you have this sort of iterative symmetry between these four Clifford algebras with different, well, they itself are not different by 4 dimensions, but by 2 to the 4th. So is this sort of the reason for this classification of J?
Yeah. Yes. 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 I mean, there is obviously a correspondence between this, and then if you remember the formula for the Clifford algebra that we had before, that is exactly because of some. I mean, what we basically got was some matrix algebra over the reals. And then there was a factor of sometimes the complex numbers, sometimes the quaternion numbers, some split versions of it sometimes, and sometimes both. So and this all reflects that this representation theory that you also see here. Yeah, good point.
Yeah.
Yeah.
I wasn't sure
So that
if
ties
maybe
to last time.
Okay. Yeah, that's nice. I thought it might be a coincidence, but it's
Yeah.
nice to know that it's related.
Right.
Yeah, okay, thanks. That's, I guess, all I wanted to know.
Good.
Any other questions? If not, I want to thank Klaus once more time, and we will see each other next week when Samuel Kováčik will have a talk.
Right. Yeah. So I think this was more or less what I aimed at. So so I don't think